There's a special type of covalent bond that's called a polar covalent bond. Now, the ones we've been seeing before were always between atoms which have similar electronegativities. So you see, this is going to be two oxygens. So they're both going to share these electrons the same because they're identical to each other. They're not going to be pulling more than the other. Each oxygen will pull just as much as the other one. Each nitrogen will pull just as much as the other one. So in this tug of war, no one wins. But what about a tug of war like this? A tug of war between oxygen and hydrogen. And I love giving this example because it's yet another story of atoms which makes sense. So oxygen is on the top of the periodic table. It's on the corner. Remember the periodic table that's over here? And you got fluorine, and you have the noble gases right there, and you got fluorine really close there. And fluorine is going to be the very, very most electronegative atom in nature. Fluorine is like, you're around me, I'll steal an electron from you. That's kind of thing it is. But we're not really worried about fluorine because fluorine is not around as often because it's like the tiger here. Sure, I'm scared of a tiger, but I know it's not going to eat me because there's not really tigers around. But I am scared of robbers, even though they're less dangerous than tigers because robbers or muggers are everywhere. So oxygen is considered the electronegative queen and fluorine is the king. But the queen shows up more often than the king does, kind of thing. Either way, you have to remember, oxygen is extremely electronegative because it's on the top right corner of the periodic table. And remember, electronegativity increases on that direction. So that means it's going to try to steal electrons from everything in its sight. So it goes to the hydrogen and says, give me that electron right now. Now hydrogen says, man, come on, I only got one electron. If I give it up to you, I got nothing. I'm not even an atom anymore. To be an atom, I got to have at least one electron and one proton. So if you steal this electron from me, I'm not even an atom anymore. So no way I'm giving it up. And then oxygen says, yes, you are. You're giving this up right now. I'm bigger. I got 6 protons here. My attraction force, my electronegativity, you've got nothing on it. I'm taking your electron. And hydrogen says, hold on a second here. You're not going to bully me. You may be more electronegative, but look at behind me. All right? I'm the most common freaking atom in the universe. So if you're going to bully me around, I'll bring it back, my friends, and we're going to mess you up. You know what I'm saying? And so my oxygen says, oh, hold on a second. There's no need to be violent now. You know, so that's the queen trying to keep her throne and appease the people. And she says, we'll share. We'll share. Don't worry about it. So we'll do a covalent bond. And so that oxygen will make a covalent bond. But now it's got 7. It's not happy yet. The hydrogen is happy because it completed the S shell, so it's good. But see, to make the oxygen happy, you're going to need another hydrogen to complete oxygen with a total of 8. And that's why you form H2O, or the water molecule, in this triangular shaped structure, because you have the 2 hydrogens connecting with the oxygen. You need 2 hydrogens to make each oxygen happy, because oxygen needs a total of 8, but each hydrogen can only share 1. Now, here's the thing. And here's why oxygen said, let's share. Oxygen knew that it was more electronegative. And it knew that even though it was sharing these electrons, okay, it knows that just like a big brother shares the toys with a small brother, it's always unequal. And so what's going to happen here is that these electrons are going to have a tendency to move towards the oxygen, which will make the oxygen end of the molecule slightly negative, and the hydrogen ends of the molecule slightly positive. In other words, electrons will tend to concentrate towards the oxygen, all right, which will basically, oxygen is cheating. She's saying, yeah, let's share, but you know what? I'll keep the electrons most of the time, kind of thing. And that creates what we call a polar covalent bond. It's a covalent bond between 2 different kinds of atoms with 2 different kinds of electronegativity. Now, the electronegativity was not different enough for the oxygen to rip the electrons apart and create an ionic bond, but it was strong enough to polarize this bond and create a polar covalent bond. Okay? Now, this bond is going to be even stronger than the triple covalent bond we talked about before. But sometimes you actually have polar bond, but not a polar molecule. For example, carbon is more electronegative than hydrogen, so it's going to be pulling electrons towards it. But you see, the one pulling this way will cancel out with the one pulling that way, so these will cancel each other out. And then those will cancel each other out. So overall, this molecule is not polar. On this one, when all the polar bonds are pushing the outside, they also cancel each other out because they're all against each other. Overall, there's no polar bond. But water is polar because you have all of them being pointing towards one direction, so you're going to have an overall direction like this. Make this side negative, and that side is going to be positive. And so that's kind of how it works, okay? So you're going to have polar bonds whenever you have a differential charge and you have an arrangement which makes an orientation of charges into one direction in the molecule. And remember, if you're doing it between two atoms which have the same electronegativity, it's going to be a nonpolar bond for sure. Now, in metals, especially those transition metals which are under D and the F block, they act completely different from the other parts of the periodic table. They're not going to be involved in things like ionic bonds and covalent bonds as often as the other kinds of metals like alkali metals and alkaline metals. All right? You're going to have more tendency for these atoms to actually get together in what we call a metallic bond. Now, a metallic bond will actually form between electrons which are actually shared as a whole between the whole thing. So in metals, they're going to be so close that the electrons on the outside or the valence shell of these atoms, which are usually have variable valence, remember that, are going to be shared among all the metals that are together forming the metallic structure. And so you see different versions of the pictures all showing the same thing. Metallic bonds are formed by sharing of electrons as a whole within the entire metallic structure. So all the metal atoms within the metal will actually be sharing these metallic bonds, which is why metals are such great conductors of electricity, because it's very easy to polarize these free electrons around in one direction, and they're floating around freely, allowing a charge to be sent through the metals. And that's why metals are such good conductors of electricity. All right? So that's the metallic bond.